evening, Prof and fellow classmates. So today I'll be presenting on Huffman coding. So what is Huffman coding? So background on what Huffman coding is first, before I jump straight into it, is that Huffman coding is a type of lossless data compression algorithm, right? So it's based off a binary tree and it uses the bottom-up approach to construct the binary tree, right? So this is one of the optimal ways of data compression, lossless data compression, right? So how it came about to be, in 1951, there was a guy called David A. Huffman at MIT that was doing a term paper to prove that the bottom-up approach is the most efficient way to construct a binary tree, right? So from 1951 up till today, is still the most commonly used method of data compression, losslessly data compression, right? So this data compression algorithm can be applied to almost anything, nearly about anything, right? So that's a picture of him, yeah. And so how is this relevant to our lives, right? So it's relevant because without data compression, files will be too big. It'll take up a lot of space on the disk. There will be all the errors coming up, and then we have to find better hardware methods to store more data instead. Also, transmissions will be better with the data compression since you have to send less data over the internet connection, right? And computers are only made possible with data compression, right? So now, what does lossless data compression mean? You'll be wondering, what does it mean? So now, so before I tell you what it means, right, I'll tell you what lossless data compression means, such that you would be able to know what lossless data compression means easier, to let you visualize what it means, right? So there's two main types of data compression. Lossy compression, which means that the original file cannot be restored after decompression. This is because the lossy data compression will remove some of the non-essential information of the file, such that the file will become smaller because the information is removed, right? So this can be done multiple times on itself, so that it can keep reducing in size by removing more and more of the non-essential information. Whereas lossless data information is the opposite of that. Lossless data information can restore itself completely after getting compressed, right? So the common file extensions are zip file, PNG, and GIF for the lossless data compression, and MP3, JPEG, and MOV for lossy compression. So I will show you an example of lossy compression, right? So in lossy compression, right, the left picture is the one without compression, and the right picture is the one with compression, right? So, right, you cannot see the difference right now. It looks identical. However, if we zoom in a picture a bit more into one of the pandas, you can see that the right one has a lower graphics compared to the left one. Can you guys see that? Right, okay, it's a lot more obvious on my computer. I'm sorry that you can't see it there. Right, yeah, if you see closely, the right is a lot more blurry. Yes. So that is the difference between, that is lossy compression. Whereas for lossless compression, there's no data loss. The picture will look exactly the same, so there's no point showing you. So for today, right, we won't be focusing on lossy compression because we are focusing on Huffman algorithm, which is a lossless compression. Yeah. So now we'll move on to the example. So an example, right, we'll start off first with so now to see what Huffman encoding actually does, right, we'll first see an encoding without Huffman's algorithm in it. So a normal encoding step, right, is to first convert the characters to AC code, and then after that change that to a binary code. Right, so it's without compression. So let's get a string, for example, right? First we separate the string into its separate characters, and then after that, from there we change it further into the AC code, which is 104, 97, 100, so on and so forth, right? So we have completed the first step. Then the second step that your computer does after that is to convert it into binary. So from here, we change it into binary code. So this is the binary code, right? It's like, it looks like a huge chunk of letters because it is, right? It's 136 bits, which is 136 characters long. That's without compression. So now we can look at an example of Huffman coding with compression, as in using Huffman's algorithm to compress, right? So the first step will be to generate a binary tree, right? So how does it do it? So the Huffman's algorithm is to count the frequency of each character appearing, and to, after that, put a stored weight equivalent to the total frequency of that character appearing onto each character, right? So, okay, do not worry. I'll show you what it means. Right, so for example, the string, there's 4 A's. There's 4 letter A, 4 letter W, and 2 space characters in the string, right? So then the weights for A will be 4, the weight for W will be 3, and the weight for space will be 2, right? So, okay, because there's a lot of steps, I will use the website to show you guys how to create a tree after counting the frequency, right? So, okay, so I'll explain the step first. The step is to assign the weighted average into a priority queue where the lowest weights are dequeued first, right? As in not dequeued, as in combined first, right? And then it prioritizes untouched trees over touched trees. Okay, you guys will see what I mean, right? Right. So you see for the string here, right? Oops, okay, yeah. So, step back. Right. Okay, so first, right, there's 2 minimum elements here. Wait. Yeah. Right? Right? So D and N, right? Depending on how the priority queue is, right? D and N is chosen first, and then after that, they will merge the 2 trees together. So the frequency, as you can see, is that A has a frequency of 4 because there's 4 characters, space has 2, and W has 3, right? So first, I'll pick the highest priority, which is the lowest frequency, and merge it together. And then now there's a new tree of value 2 inserted back into the priority queue, right? But this 2 is actually something like 2.5 because those untouched trees are prioritized first compared to this touched tree, right? So they'll move on, and then they'll choose the next one with the lowest value, which is 1 and 1 again, I and L, and then they'll merge it together to form another root tree of 2 and put it back in the priority queue. So right, now we let the animation play, and you can see that it automatically merges, right? And then that's where, right? Yeah. That's where you see this, right? Where they choose the untouched 2 and the touched 2 tree, right? And merge it together instead of 2 trees which are already touched, right? Because the space character is untouched. So they prioritize that first compared to these 2 and these 2. So they pick this one and this one. So then they merge to form 4, right? Then they merge all the low ones, then they merge 4 and 4, and 5 and 4, and 8 and 9, right? So this is the tree, right? Okay, right? So now that we have formed the tree, right, according to the rules, right? So we are done with generating the binary tree for Huffman coding, right? So next is to generate the encoding table to decompress the thing, to decompress the tree, right? So read every left traversal as 0 and read every right traversal as 1 for Huffman coding, right? So for example, right? Okay, so how to encode it is a space will be 0, 0, 0 because it travels left 3 times. So it's 3 left traversals, which is 3 zeros, right? And then H is 0, 0, 1, 0, which is 2 left traversal, 1 right traversal, and 1 left traversal, right? So then after we get all this, our encoding table, we can change it. So we know from the previous one that H is 0010, and then here 0010 is the first one, and then A is 10, and then D is 0100. So then it compresses it by reducing it to 55 bits. So comparing both of it, right, the compressions looks really good, right? 136 bits and 55 bits. And then furthermore, this is lossless data compression, right? So that means that you can get back the exact string from just these 55 bits as compared to the 136 bits. Yeah. So 0, 0, 0, 1, 0, 1, 0, 0, 0. So basically this can be decompressed by going through the tree using the binary tree here, right? So how it does is recursively, right? It will iterate through the string. So is 0 a character? If not, then go down to the left. Then it goes down to the next character of the string, which is 0, 0. So is 0, 0 a character? No. Then it moves down further down to 0, 0, 1. Then is 0, 0, 1 a character? No. Then after that, so and so forth, eventually till it reaches H. Then you'll remove the first 4 characters and H will be printed out. However, knowing this, Huffman coding is actually not that impressive for short strings because the amount of space that it needs to serialize the binary tree and to generate the binary tree is actually longer than it requires us to actually have the 136 bits to 55 bits advantage, right? Because the binary tree will cost quite a lot of space also, right? So this one, so Huffman coding might sound good, like 136 bits to 55 bits, but actually, right, it's not as great as it sounds, right? So, like, right, have to add a tree to the start of the file. So even though the file is compressed, the size might be larger for shorter strings. Yeah, and so that concludes my presentation for Huffman coding. Yeah, thank you.
Anyone have any questions for Benjamin? Do you guys have a question? Yes, a question.
What's the complexity of
Complexity, or?
just kidding.
Maybe that's the final exam question, right? Alright guys, so we have a survey form on eLearn. So maybe if you guys can take a couple of minutes to do that before we move on to the next part.